Space is a hostile place. Weightlessness is the least of your worries when traveling through it. Closed environments, distance from Earth, isolation, and radiation can all considerably impact human health. Long-term studies have all concluded that all matters mentioned can inevitably trigger behavioral issues. Issues that may cause significant impact to the outcome of the mission. At millions of kilometers away from Earth, any problem can become deadly, and turning back home is definitely not an option. The expected travel distance from Earth to Mars is about 112 million kilometers. Launch periods are restricted to once every 26 months. When the time comes, it takes about 9 months to reach Mars at the lowest energy requirements. A round trip would involve 500 days waiting period on Mars for the next window to travel back to Earth, totaling 1,040 days. Throughout the trip, astronauts are expected to receive 0.66 sieverts of radiation exposure, which is equivalent to 2.6 million airport security screenings. Working as a flight attendant for 440 years, 22 full-body CT scans, or living on board the ISS for 4 years straight. 1 sievert is the maximum dose allowed by NASA for astronauts during their entire career. Anything more, and damage is irreversible. 5 sieverts and you're dead. On top of that, the effects of zero-G force on the human body gets worse the longer you stay in space. 6 months is when you really start to see the problems. Your arteries become rigid as though you've aged 20 years, along with blood flow problems, bone density loss, and eyesight impairment. Traveling to Mars is definitely one hell of a trip. Hello everyone, Subject Zero here. For decades, we relied on chemical rockets to take us to space. They work fine for relatively short distances, like going to the moon, delivering satellites to orbit, or even humans to the International Space Station. As we envision going beyond, chemical rockets become more of a limitation than anything else. It all comes down to the maximum exhaust velocity that can be achieved by a chemical reaction. Rocket engines work with basic principles, such as Newton's third law of motion. For every action, there is an equal and opposite reaction. Chemical rockets use hot gases that are created by chemical combustion, such as hydrogen and oxygen, to create thrust. A way to visualize this would be with a shotgun, where instead of bullets, we use molecules. If we take into account the mass of these molecular bullets and their velocities, we can calculate thrust using the following equation, where F is the thrust measured in newtons, m dot is the mass flow rate in kilograms per second, and v is the average exhaust velocity in meters per second. What this equation shows is that to maintain thrust constant, we can either increase mass flow rate and decrease the average exhaust velocity, or the opposite. To be successful, good thrust levels are required while consuming the least amount of fuel possible. Chemical rocket limitations can be seen in current technology. The SpaceX Falcon 9 first stage can produce 7.6 million newtons of thrust. Using the thrust equation, we can calculate how much mass is being expelled by the first stage of the rocket on average. About 2,496 kilograms per second, which depletes the first stage in only 174 seconds. That is enough to take 22,800 kilograms of payload to low Earth orbit, or 8,300 kilograms to geosynchronous orbit. Sounds like a lot of cargo, but that is only a fraction of the total weight of the rocket, about 4% and 1.5%. High exhaust velocity is key for performance since you can accomplish space missions with less propellant. Therefore, less fuel, lighter spaceship. The problem is, how do you increase exhaust velocity? Nuclear propulsion success can be derived by one simplified thermodynamic equation for exhaust velocity. Exhaust velocity is proportional to the square root of the absolute temperature divided by the molecular mass. What this equation shows is that the lighter the molecular element, the higher the exhaust velocity will be. Thus, hydrogen becomes the fuel of choice for nuclear propulsion. The big difference here is that chemical rockets rely on the energy available from the chemical reaction itself. To demonstrate this, let's use the average temperature of most rocket engine chambers, that is about 3000 Kelvin. If we consider the speed of water expelled from the main engine of the Space Shuttle orbiter, m equals 18, we will have a gain of almost 3 times the speed with hydrogen, m equals 2. However, increasing exhaust velocity comes at a cost. Where can we get the required power from? In late 1960s, early 1970s, nuclear thermal rockets were fully developed and tested under programs such as the Nuclear Engine for Rocket Vehicle Applications, aka NERVA. This program was just one of the 2 categories that study nuclear propulsion. In this project, they developed a solid core reactor based on uranium zirconium carbide-graphite matrix. There were 4 main configurations tested with increased thrust levels. The largest NERVA-derived engine produced approximately 112 kilonewtons of thrust. The fuel element was a complex mix of gadolinium oxide and uranium oxide particles distributed along a tungsten matrix. Each fuel element was hexagonal in shape with 19 coolant passages. A total of 564 fuel elements and 241 tight tubes were used with a total mass of 2,645 kilograms, containing 36.8 kilograms of uranium-235. It delivered a thermal power of 555 megawatts. Just like in conventional rocket engines, the nozzle is cooled by hydrogen that comes in through the inlet valve. It is then transported upwards to the outside of the reactor towards turbopumps that increase its pressure. At the same time, a second flow of hydrogen is pumped into the tight tubes, which further increase temperature and pressure. This flow is added to flow number 1 and is directed towards the second set of turbopumps. In this last phase, hydrogen goes back to the core, passing through the fuel elements where it experiences the largest increase in temperature, from 367 Kelvin to 2794, with a mass flow rate of 12.6 kilograms per second. A quick comparison with the average flow rate of the Falcon 9 rocket at 2,496 kilograms per second, and it makes it easy for us to understand why nuclear is the best choice for space travel, not lifting large payloads into space. Why should we consider the nuclear option? To travel to Mars, I am considering a ship that is 220 tons, plus the necessary fuel mass to accelerate the ship. That is roughly 2 times more massive than a space shuttle orbiter. This will give enough room for astronauts to have a comfortable trip. If we were to use 4 chemical rockets delivering 30 million newtons of thrust, like the Falcon 9, to propel the ship, and assuming it will be accelerated from the ISS orbit to its final velocity, the ship would generate 15.6 meters per second square of acceleration, whereby the end of its burn time would achieve a final velocity of 10,372 meters per second. With this speed, reaching Mars would happen in 125 days, or 4.2 months. It seems like a good choice, but there is a problem. To reach that speed alone, the total fuel mass is already 1.7 million kilograms. Making a very simple calculation, assuming that the same amount of fuel will be needed to decelerate the ship and travel back to Earth, we would need 7 million kilograms of fuel. That is 31 times the mass of the ship where the astronauts are located. Following the same logic for nuclear propulsion, the best proposed and tested nuclear core, the Phoebus 2A, gave an output of 930 kilonewtons, with a flow rate of 120 kilograms per second. With 4 engines and 3.7 million newtons of thrust, our spaceship would have an acceleration of 3.6 meters per second square. The difference here is that these rockets can burn fuel for longer times, thousands of seconds. The best engine had a burn performance of 109 minutes. If we were to use just half of that time for our spaceship, we would get a final speed of 15,000 meters per second, which would make to Mars in only 3 months with less than half the fuel, or 818 tons. Making the same assumptions as before, the total fuel needed would be only 3.2 million kilograms, only 15 times the mass of the main ship. The problem is always dealing with radioactive materials. After all, for this to work, uranium-235 purity would have to be high, which means nuclear weapons territory. Although the engine cannot be turned into a nuclear weapon, nor would explode like one, we still have to consider that if the rocket does explode, highly radioactive elements would contaminate everything around it. If it happens in space, no big deal, but getting the engines to space is where the problem lies. Regardless, in the near future, thermonuclear propulsion is the best choice by far if we really want to colonize Mars. Now, if SpaceX or any other private company will be able to use this technology remains to be seen. Alright folks, that's it, we're done here.